So let's now consider the lower Riemann sum of our function f plus g and try and derive an inequality for this in terms of the lower Riemann sum of f and the lower Riemann sum of g. So by definition, this is the sum from I is equal to 1 to n of xi minus 1 times the infimum x is allowed to vary over xi minus 1 to xi of, and then it's f plus g of x, but of course we know that that's f of x plus g of x by definition. So again, we want to split this into the infimum of f of x plus the infimum of g of x. Now again, it's not going to be an equality, instead it's going to be an inequality, and the inequality this time is going to be the opposite way round, so this is always going to be greater than or equal to the infimum of f of x. X is an element of that interval, xi minus 1 to xi, plus the infimum of g of x, where x is an element of that interval, xi minus 1 to xi. Now, to get some informal intuition for this, we can informally think of this just as the minimum. Now, of course, infimum is only equal to the minimum for nice functions that actually do obtain their minimum. However, for intuition, it's nice to just think of those functions. So let's imagine that being the case. So just replacing this complicated thing with minimum. So this is the minimum of f of x over that interval. So the smallest value that f obtains anywhere on that interval. This is the smallest value of g of x on that interval, so the smallest value g of x obtains over that interval. Then we're adding them together. If you then think about the function f plus g, what's the smallest value that it's going to obtain over that interval? Well, it must be greater than or equal to this, and it's only going to be equal to this if it happens to be the case that somewhere on this interval, f and g both obtain their minimum values at the same place. If it's the case that they don't obtain their minimum values at the same place, then the minimum of this won't be equal to these two added together. It will be strictly greater than it, because at any place where f obtains its minimum, g isn't obtaining its minimum, so it will be bigger than this. And at any point that g obtains its minimum, f won't be obtaining its minimum, so it will be bigger than this. And at any point where neither of them are attaining their minimum, both of them are going to be bigger than this. So that's sort of the informal intuition, but let's now do it a bit more formally as we did in the previous video. So the formal argument is just the mirror image of what we did in the previous part. So here, this is the infimum, the greatest lower bound of this set of values of f of x plus g of x over that interval. So again, just to help, I'll write that set down. So it's f of x plus g of x, all values of that, where x varies over this interval xi minus 1 to xi. So that's a great big set of values, the set of all values that the function f plus g obtains over this interval. And this number here is the infimum of that, so it's the greatest lower bound. So if we want to show that this number is less than or equal to this number, it would suffice to show that this is a lower bound for this set, because any lower bound is always going to be less than or equal to the greatest lower bound by definition. So if we just show that this number here, this plus this, is a lower bound for this set, i.e. that it's less than or equal to everything inside this set, so for all x in this interval, f of x plus g of x needs to be greater than or equal to this, then we'll have done. But of course that follows really simply, because this number is the infimum of the values of f of x over that interval. So for all x in that interval, f of x is going to be greater than or equal to this. And this value here is the infimum of g of x over that interval. So for all x in the interval, g of x is going to be greater than or equal to this. So whatever x you take in this interval, f of x is greater than or equal to that, g of x is greater than or equal to that, so combine those two inequalities together and you'll get that f of x plus g of x is greater than or equal to this. And that's the case for all elements in that interval. Therefore, everything in this set is greater than or equal to this, hence it is a lower bound, hence it must be less than or equal to the greatest lower bound here. Now that inequality that we've derived there, holds true for all the intervals that you've partitioned the original interval AB into. So now what we can do is we can say, whoops, not like that, for all I is equal to 1, 2, all the way up to n, and we'll take the inequality and once again we'll multiply it by xi minus 1. So, whoops, and I'm about to write down supremum rather than infimum. So xi minus 1 times the infimum, x is an element of xi minus 1 to xi of f of x plus g of x is going to therefore be greater than or equal to, and then we'll distribute the multiplication over the addition. So we'll get xi minus 1 times the infimum of f of x is an element of that interval, xi minus 1 to xi, plus xi minus 1 times the infimum of g of x is an element of the interval, xi minus 1 to xi. Brilliant. And that inequality holds true for every single one of them. So you could put in I is equal to 1, I is equal to 2, I is equal to 3, all the way up to I is equal to n. That then allows us to combine them together in a sum as we did previously to get lower Riemann sums. So again, if all of these things are greater than or equal to the things on this side, if we add all of the things on the left up and all of the things on the right up, then that sum of the things on the left is guaranteed to be greater than or equal to the sum of the things on the right. So, well, of course, once we sum from I is equal to 1 to n, these things, that will be the lower Riemann sum over our dissection of the function f plus g, and that's going to be greater than or equal to, and then split the two sums up. So we've got the sum of this, which is the lower Riemann sum over our dissection d of f, and then sum of this from I is equal to 1 to n is the lower Riemann sum over our dissection of g. So there we have it. There is our inequality for the lower Riemann sum of f plus g. So now what I want to do is actually combine this inequality with the one that I got for the upper Riemann sum together to make a huge inequality, a 4-part inequality. So right on this side we've got the lower Riemann sum of f plus the lower Riemann sum of g. That is less than or equal to the lower Riemann sum of f plus g, which is less than or equal to the upper Riemann sum of f plus g. That's just an inequality that holds true for all upper and lower Riemann sums of it, whatever function you take, which is less than or equal to the upper Riemann sum of f plus the upper Riemann sum of g. And we are going to use this inequality to prove that the function f plus g must be Riemann integrable using the Riemann integrability criterion. So to prove f plus g is Riemann integrable using the Riemann integrability criterion, we must show that for all epsilon greater than 0, there exists a dissection D such that the difference between the upper Riemann sum and the lower Riemann sum is less than epsilon. So the Riemann integrability criterion, remember, is an if and only if statement. So a function is Riemann integrable if and only if the Riemann integrability criterion is met. The two are equivalent criteria. So by showing this, we show that our function f plus g is Riemann integrable. And what it's really saying is that you must be able to make the difference between the upper and lower Riemann sums indefinitely small by taking finer and finer dissections. So, how are we going to show this? Well, we're going to let epsilon be greater than 0, and I'm going to show you how to find such a dissection. Now, how am I going to do it? Well, I'm going to use this inequality and the fact that f and g are Riemann integrable and therefore they obey the Riemann integrability criterion. So starting with f, because f is Riemann integrable, I can find you a dissection and we'll call that dissection 1 such that the upper Riemann sum over that dissection 1 minus the lower Riemann sum over that dissection 1 is less than, now I'm not going to choose epsilon, instead I'm going to choose epsilon over 2. And hopefully it should be obvious to you, hopefully you've done enough analysis to understand why I need it to be epsilon over 2. It's because I'm also going to do it for g, and it's also going to have a difference less than epsilon over 2, and then when they're added together, it will give that it's less than epsilon. So just to explain again where this inequality came from, so because the function f is Riemann integrable over the interval ab, it obeys the Riemann integrability criterion, and therefore I can find dissections such that the difference between the upper and the lower Riemann sums are indefinitely small. In particular, I can take this positive number, epsilon over 2, and I can find a dissection which we've called d1 such that the difference between the upper and the lower Riemann sum for f over that dissection is less than epsilon over 2. So that's where that inequality came from. Now, I can do the same thing for g. So I can find a dissection, and it isn't necessarily going to be the same dissection, so I'll call this dissection d2, such that the difference between the upper and the lower Riemann sums for g over that dissection is again less than epsilon over 2, and that holds true again because g is Riemann integrable and therefore obeys the Riemann integrability criterion. So I'm just using the Riemann integrability criterion with a tiny number epsilon over 2 here. Now this looks very hopeful because it's making us think that we can bound the difference between this thing here and this thing here, and therefore sandwich these things in between and make sure that the difference between them is going to be less than epsilon. So it's looking very hopeful. There is, however, one thing stopping us from being able to do that, one thing standing in our way, and that is the fact that we have got two different dissections here. You see, this inequality only holds true if we're talking about the same dissection everywhere, and at the moment, these two are different dissections, so that's no use at all. So what we now need to do is construct a refined dissection, which we'll call d bar. So it's the refinement of d1 and d2. So you take all the cuts that are in d1 and you take all the cuts that are in d2. Some of the cuts may be shared, but the ones that aren't shared, you need to put them all together and produce a new dissection. So this dissection d bar, it contains every single one of the cuts in d1 and it contains every single one of the cuts in d2. It is a common refinement of d1 and d2. Now, these inequalities that I've got here, my precious inequalities, are still going to hold true with this refined dissection, because remember, something that we proved back in the video on Riemann integration is that the more refined you make a dissection, the better it becomes. So what we know is if you have the lower Riemann sum of d1 of f, it will be less than or equal to the lower Riemann sum of this refined dissection of f, which will then be less than or equal to the upper Riemann sum, because all lower Riemann sums are less than or equal to upper Riemann sums, of the refined dissection of f, which will then be less than or equal to the upper Riemann sum over d1 of f. So this inequality holds true no matter what dissection you have here, as long as this one is a refinement of this one. So when you take a dissection and you take a refinement of it, the lower Riemann sum gets better, so it goes up, or it might stay the same. I mean, it might be the case that this dissection actually hasn't improved it at all, but it certainly doesn't make it worse. It only makes it better or it stays the same, and getting better for a lower Riemann sum is going up, and then equally, the upper Riemann sum gets better or stays the same when you refine the dissection. So upper Riemann sums come down when they get better. So refinements always make the upper and the lower Riemann sums better. They make them more accurate, captured by this inequality here. So now, if we know that the difference between this one and this one, which is this minus this, is less than epsilon over 2, well, these two are sandwiched in between there. You can imagine them on a line, and in fact I've written them in a line here. So the gap between this one and this one must certainly be less than epsilon over 2 because of the fact of how it's sandwiched in between these two. where the gap between them is less than epsilon over 2. So in fact, I might just draw a picture here. So we have these four numbers kind of like this, and if the gap between these two, the end ones, is less than epsilon over 2, then the gap between the two inner ones is certainly going to be less than epsilon over 2. Now we could do that. We could, arduously go through all the ordered field algebra there, but I think, by this stage in the playlist on real analysis, we're very familiar with these inequality properties, so we won't go through the laborious field algebra process of proving that. So, the upper Riemann sum, therefore, over this refined dissection d bar of our function f minus the lower Riemann sum over d bar of f is going to be less than epsilon over 2. And similarly, because it's a refinement of d2 as well, it's a common refinement, remember, we also have that the upper Riemann sum of g over d bar minus the lower Riemann sum of g over d bar is less than epsilon over 2. And now we're ready to combine them all together. So d bar is going to be the magic dissection that makes the gap between the upper Riemann sum and the lower Riemann sum of f plus g less than epsilon. And to show you how this all fits together, I will actually go through the laborious inequality manipulation. So we'll start with this inequality here. And remember, we are trying for something of this form, so it would make sense to subtract from both sides this thing. So just to highlight this, we are taking this inequality and we're going to subtract from both sides that bit. And that will give us the upper Riemann sum of f plus g. Oh, and by the way, we're doing this now all over d bar. So this inequality, this great big four-part inequality here, this held true no matter what dissection you have. So in particular, it holds true for our refined dissection, our common refined dissection d bar. So upper Riemann sum over d bar of f plus g minus the lower Riemann sum over d bar of f plus g is going to be less than or equal to the upper Riemann sum of f over d bar plus the upper Riemann sum over d bar of g minus the lower Riemann sum of f plus g over d bar. Excellent. Now this bit isn't what we want yet. It's not what we want. So we're going to use this bit now to get something to replace that with using transitivity. So the way we're going to do this is firstly we're going to multiply both sides through by -1 so that we've got minus this thing here, and then we're going to add this onto both sides, and you'll see how wonderful this works. So I might make a bit more space here. So bringing inequality in red out here, we've got minus, everything's multiplied through by minus now. So minus the lower Riemann sum, and everything's still over the dissection d bar. I apologise if I miss any of the bars anywhere. Please, if I write d anywhere, replace it with d bar. So minus the lower Riemann sum of f over d bar minus the lower Riemann sum of g over d bar. Now we've multiplied through by -1, so the inequality has to flip minus the lower Riemann sum of f plus g over d bar. Excellent. Now we're going to add this bit onto both sides, because then this thing will become this thing and we'll be able to apply transitivity. So let's add those onto both sides. So upper Riemann sum over d bar of f plus the upper Riemann sum over d bar of g. So that's all one side there, and I'll circle that in a yellow box, is greater than or equal to upper Riemann sum over d bar of f plus the upper Riemann sum over d bar of g. And of course this thing here, it might be written the other way around, but it's the same thing as here. So we have that this is less than or equal to this, and this is less than or equal to this. So by transitivity, we now have that this thing here is less than or equal to this thing here. Now let's write that out. So this is our desired bit, the upper Riemann sum over d bar of f plus g minus the lower Riemann sum over d bar of f plus g. This is the bit we're really interested in. We desperately want to bound the size of that. We want it to be less than epsilon. And what we know is that it's less than or equal to the upper Riemann sum over d bar of f. I'm just going to rearrange bits. I'm just going to put the appropriate bits together. So putting these two bits together, so we've got the upper Riemann sum of f over d bar minus the lower Riemann sum of f over d bar plus the upper Riemann sum of g over d bar minus the lower Riemann sum of g over d bar. And now, of course, we use our inequalities over here. So, add those two inequalities together, combine them together. So this is strictly less than epsilon over 2. This is also strictly less than epsilon over 2. So if you add this to this, which is what we've got over here, you're going to get something that's strictly less than epsilon. So this is strictly less than epsilon, and therefore by transitivity, the upper Riemann sum of f plus g over d bar minus the lower Riemann sum of f plus g over d bar is strictly less than epsilon. So I have shown you then a way to construct a dissection such that the difference between the upper and the lower Riemann sum is less than this value epsilon, and that holds true no matter what epsilon you pick. Any positive number epsilon, I could have done this. This construction of the d bar dissection for which this inequality holds true would have worked no matter what epsilon you pick. Therefore, it is the case that for all epsilon greater than 0, there will exist a dissection such that the difference between the upper and the lower Riemann sum of f plus g for that dissection is less than epsilon. Hence, the function f plus g satisfies the Riemann integrability criterion and is therefore Riemann integrable over the interval ab. We'll have a break there, and in the next part we will prove that the actual value of the integral is equal to the value of the integral of f plus the value of the integral of g.